let's talk about finding the area between two curves. So what we already know is that if we have a continuous function on a closed interval from a to b, that the area under that function can be found by simply taking the integral. That comes out of calculus 1 and from a Riemann sum. We developed that idea of the Riemann sum giving us the area. We take the limit and we define what's called the definite integral. And now we have the ability to compute the definite integral using the fundamental theorem of calculus and what we know about integrals and evaluating them. So we already know how to find the area under a curve. How do we find the area between two curves? So if we have two curves, how do we find the area between them? So here's two pictures, and it turns out our curves can be defined as functions of x. So in this first picture, these are functions of x. Y equals f of x, y explicitly defined as a function of x. And over here, we could also talk about finding the area of two regions where they're bounded between two functions that are defined in terms of y. So functions of y. So notice here, these are x equals a function of y. I used f of y, but we also have g of y on the board as well. So the process for finding the area of the regions doesn't matter which orientation they are, if they're a vertical orientation or a horizontal orientation, because either way, we're going to go back to this idea of Riemann sums, and we're going to set up a Riemann sum. So in this first video, I want to go through the Riemann sum real quickly so you'll see where it comes from and do one quick example. So here we go. So let's start off here with given two functions. And for our purposes here, we will have them be functions of x. So given two functions, y equals f of x and y equals g of x. And in this case, we will say where, so it'll match the drawing, f of x is greater than or equal to g of x on an interval from a to b. So that's exactly the picture that we have right there. So we have that picture. It looks something, if we were to draw it without it, I've kind of got this nice little picture here. If we wanted to find the region between those two, so here's f of x and here's g of x and here's a to b. If I wanted to find the region between those two, what I'm going to do is I'm going to divide up. So here's just a little reminder of Riemann sums. To find the area, this is a common theme we're going to see in Calculus 2. Anytime we want to find something, area, volume, whatever it is that we're looking for, one of the physics concepts like work or force, what we're going to do is we're going to take the interval that we're looking at, we're going to divide it up into smaller chunks. So to find the area, what we're going to do is we're going to divide the interval from a to b into n subintervals, each of width delta x, which is going to be b minus a over n. And you can see that up in this little picture. So we take a to b, we're going to divide that up into n little subintervals. Each one of these little subintervals is going to be of a width, we're going to call it delta x. So we're going to divide that interval up into n subintervals, each of width delta x. Then on each one of those subintervals, so now on each subinterval, call it the ith, so generically we're going to call it the ith interval, we are going to find the area of a rectangle. Well, the area of a rectangle is the easiest area to come up with. So those are already drawn in on this picture. So in each of those little subintervals, we're going to divide up this total area that we want into a bunch of rectangles, into n rectangles. So we divide them up. How we build those rectangles is going to come from finding their height for some value on the subinterval. So in each of these little subintervals, we're going to pick some tag. So on the x sub I minus 1, x sub I interval, pick a tag. Going back to calculus 1 when we do Riemann sums, a lot of times we pick the right-hand endpoint, sometimes we pick the left endpoint, the midpoint, but it doesn't actually matter. I'm going to call that tag just x sub I star. It doesn't matter. Just pick any tag in that interval, x sub I minus 1 to x sub I. Pick any tag in that interval, then the area of the ith rectangle, that looks like the ith rectangle. So in each of those little subintervals, let me see if we can get that picture back up here one more time. So in each of those little subintervals, let's pick this guy right here. On each of those little subintervals, the height of that rectangle right there is going to be the height of the function on top minus the height of the function on the bottom. Well, in the way we drew it here, because f of x was greater than or equal to g of x. F of x is the function on top, so it's going to be f of x sub I star minus g of x sub I star. So the area of the rectangle is going to be f of x sub I star minus g of x sub I star times, that is the height of each rectangle, times the width. While I'm in red, let me write width times the width. And the width of each rectangle is delta x. They all have uniform width. So that's what the area of each of those individual rectangles looks like. Let's just bullet. This is the process we go through. We divide it up. On each of those subintervals, we pick a tag and we find the area. Now, how do we actually find the total area? So how do we actually find the area? I'm going to actually go down just a little bit further. Scroll out just a little bit, keep it all up there. How do we find the area of the region? Well, it would be approximately equal to the Riemann sum from I equals 1 to n. If we added up all those rectangles, f of x sub I star minus g of x sub I star times delta x. But we don't want an approximation. We want an exact area. So how do we make it exact? Well, we just take the limit as the number of rectangles goes to infinity. As we shrink down the width of each rectangle, as we shrink down, another when we say n goes to infinity, what that automatically does is it makes delta x go to 0. It makes the width of the rectangles go to 0. So let's zoom in. If we want this actual area, right, we want to fill in this area, well, we need to just make the width of each of these rectangles go to 0 so they get infinitely small. Let me get rid of some of my drawings here. And so that's what we do. We let the number of divisions down here from A to B, we let the number of divisions go to infinity, shrinking that delta x right down, and that gives us the area of the region between f of x and g of x. But more importantly, this is the definition of a definite integral. This is how we defined the definite integral. So this is actually equal to, grab my pen again, not my highlighter. This is actually equal to the integral from a to b of f of x minus g of x dx. And that is where our formula for the area between two regions where f of x is greater than g of x comes from. So that's the development of the formula. I'm going to go ahead and go over to its typed up version, but I wanted you to see where it comes from. Anytime we want to calculate something in calculus using integrals, we're going to divide it up into smaller chunks. We're going to create the Riemann sum, and we're going to figure out what the definite integral that would correspond with what we're looking for is. Okay, let's go to the official definition and do one quick example. Okay, so if we want the area bounded by two continuous curves, f of x and g of x, where f of x is greater than or equal to g of x, and I want to talk about that subnotation I added in here. Notice here that I have y sub t and y sub b. I gave our y, our functions, a little bit of extra notation to denote which is the function on top. So since f of x is greater than or equal to 0, y sub t denotes the function on top, and y sub b denotes the function on bottom, or the smaller of the two functions. F of x is greater than or equal to g of x in this definition. So in my little picture that I drew over here, this function, f of x, is the function on top, and g of x is the function on bottom because it is smaller. It is below f of x. So that's y sub b in the notation. If that is the case, if those functions are defined as such on the interval from a to b, then the area between those two regions is the integral from a to b of f of x minus g of x dx. And shorthand notation, you can write the integral from a to b of y sub t minus y sub b, and I will use that notation. Okay, it can often be helpful to draw a representative rectangle when we are doing our areas to see which function's on top and which function's on bottom. So come to your area, draw a little rectangle. Remember, this integral comes from looking at a Riemann sum of the areas of rectangles. So draw a little rectangle, and then you'll be able to see in the height of that rectangle which function's on top and which function's on bottom. We'll show that in this example as well. Okay, let's keep our formula up there on the board if we can. I need to zoom in a little bit. Okay, so let's say, find the area of a region. We had two functions given, y equals the square root of x plus 2, y equals x, and x equals 0. If we want to find these functions, just some general rules of thumb. We're going to want to draw the region. If it's not already given to us, draw the region, or if we need to, use some sort of technology like Desmos to graph the region, but draw the region. And secondly, determine any bounds. So determine the bounds. Sometimes that will require us to find intersection points. Sometimes the bounds are given, but a lot of times we have to figure out where the two graphs or where the two functions are intersecting. Find intersection points. All right, so for this particular graph, we have, these are two graphs that we should be able to graph really easily. Y equals the square root of x plus 2. That's just the square root function, shifted up 2 units, and has this kind of general shape. Okay, that's y equals the square root of x plus 2. Now, y equals x, well, that's just the graph that looks like that. It goes this way as well. The square root function actually starts at 0. It's only defined for x is greater than or equal to 0. All right, so this function right here is y equals x. It's just the graph through the origin with a slope of 1. I could have pulled out a ruler, but we get the general idea. And x equals 0 is the horizontal line where x, or I'm sorry, the vertical line where x equals 0. So obviously that's this bound. I know it's kind of hard to see. Maybe I'll draw it in. Oh, grab my red pen. I'll draw that one there. So this is the region of area that we want to find. Okay, so that said, we do know that this bound here is 0, but we need to figure out what this intersection point is. I think my scale might be a little bit off here, but we need to figure out what that intersection point is. So the first thing we'll do here, and we could kind of guess and check on this one. If I had actually drawn it a little bit better to scale, we would be able to see it. But let's go ahead and do it down here. So the intersection points. The intersection points of these two graphs, we just set them equal to each other. The square root of x plus 2 equals x. Use a little bit of algebra here. So isolate the square root, x minus 2, square both sides. Remember, when I square both sides, I have the potential to create some extraneous solutions. We'll talk about that in just a second. Minus 4x plus 4. And then let's go ahead. Oops. This should not. That should just be x. There we go. X equals x squared minus 4x plus 4. Let's just subtract that x over, so we get x squared minus 5x plus 4. That's a quadratic that does factor, so that makes it nice for solving. And x equals 4 and x equals 1. Okay, now I'm looking at this graph and thinking, well, one's somewhere in here. That doesn't seem right. Like something seems wrong. And that's why I wanted to just remind you, right? We have to remember all of our algebra. Remember right here in this step, I can end up with extraneous solutions when I square or raise an equation to any power, actually. I can end up with extraneous equation or extraneous solutions to the original equation. So we do have to check. So let's just go back real quick, follow through the algebra. Let's check for extraneous solutions. And in this case, if I plug x equals 4 back into the original, I get the square root of 4 plus 2. 2 plus 2, does that equal 4 is the question? Yes. So that's a solution. X equals 1 was our other possibility. If I plug that back into the original, square root of 1 plus 2, does that equal 1? No. That is not a solution. So that guy was an extraneous solution. So a good little review of algebra there. But 4 is a solution. And I know my scale is not perfect, but I'm not going to redraw this. This is at 4. So my scale on the x-axis is just a little bit off. But that bound right there is 4. So when we're doing this calculation to find the area of this region, the first thing we do, draw the region. Next, determine the bounds. Set up the integral. So set up the integral to find the area. And while I'm at it, I'm going to go ahead and just write my last bullet here. And then the last thing is integrate. Right? Use our actual skills of integration to do it. So let's get this set up. So what is the area on the interval from 0 to 4 now that we found the bound? So we're going to be integrating from 0 to 4. We want to take the function on top minus the function on bottom and integrate with respect to x. So this is where drawing a little representative rectangle, right, on let's zoom in a little bit and clean up my rectangle. This is where drawing a representative rectangle can be helpful. So there we go. There is a rectangle. Its width is going to be delta x, and its height is going to be the difference between this function on the top minus the function on the bottom. So the function on the top is clearly this square root function. I'm going to move it. It's over, kind of got over here with the words. Let's move it over here. Here's the function on the top. This is y sub t, and this is the function on the bottom. So when we set this up, that's why drawing that rectangle can sometimes, if it helps you to visualize it, drawing that rectangle can be helpful. So this is the integral from 0 to 4 of the square root of x plus 2, function on the top, minus the function on the bottom, x, and we're integrating with respect to dx. That in the Riemann sum, that delta x became our differential dx. All right, and now we can find the area by simply doing that integral. This is going to be a basic integral here because the square root of x we could think of as, this is the same as writing that as x to the 1/2. And let's just go ahead and do this integral and do the calculation. So when we integrate x to the 1/2, this becomes x to the 3/2 divided by 3/2. So that's multiplying by 2/3 plus 2x minus x squared over 2. And we're evaluating it from 0 to 4. So we end up with 2/3 times 4 to the 3/2 plus 8 minus 16 divided by 2. So we end up with 2/3 times 4 to the 3/2 is the square root of 4, which is 2 cubed. So that's times 8. We get 8 minus 8. Those cancel out. And we end up with 16/3 for this area. Now, I'm going to go ahead and write this. I'm going to say unit squared or u squared because that reminds us that what we just calculated was an actual area. It's a number of units. So we just calculated the area of this, red region I have over here on the board. All right, let me try to get it all on the screen if you wanted to screenshot it. And let me just remind you, as we were going through it, I was outlining these steps real quick. And these are the steps we want to go through. We want to draw the region if it's not already given to us, determine the bounds from A to B of the region. meaning sometimes we're going to have to find intersection points if those bounds aren't given, set up the integral to find the area, right? And then actually integrate. Okay,